We consider the symmetric group Sn of permutations of a set of n elements. Moreover, we consider the symmetric group algebra, which are these elements, these permutations, with coefficient, which is a complex number. You can easily multiply these linear combinations. Now, the idea here is to construct a ring, which is associated to a filtration of this group algebra. And then the filtration gives rise to a graded ring, which will be the Farahat-Higman ring. So what is the degree? Well, the degree Q of a group element sigma is equal to the number n in Sn minus the number of cycles in the permutation sigma. So for example, the degree of a k cycle will be equal to k minus 1. It is not too difficult to show that the degree q is actually the minimal number of transpositions that one needs to make up sigma. So for instance, for a 3 cycle, we would need 2 transpositions to make it. Clearly then, q is a length function. In other words, the degree of the product of 2 permutations is smaller or equal than the sum of the degrees of the separate permutations, because this will be made of a number of transpositions which are smaller or equal than the number of transpositions that make up sigma 1 and sigma 2. Let's now consider a subalgebra of the symmetric group algebra, which is the center of the symmetric group algebra. The center is generated by conjugacy class sums. So we define conjugacy class sums, which are nothing but the sum of all elements rho which sit in the same conjugacy class as sigma. We sum them with coefficient 1. The conjugacy class sums satisfy the conjugacy class algebra, which can be denoted as follows. It has structure constants f, sigma 1, sigma 2, sigma 3. It is not too hard to understand that these structure constants are polynomials in the number n, related to the order of the symmetric group. Now, if we imagine that Sn acts on the set 1, 2, 3, all the way to n, then we can define the number of active colors or entries in this set Pn active under the pair sigma 1, sigma 2. This is the number of active entries in Pn under the pair sigma 1, sigma 2. Similarly, we can define the active colors under the permutation sigma 3. Now, the structure constant f are polynomials of degree equal to the number of active colors in the pair minus the number of active colors in the right-hand side permutation. Why is this so? Well, the n-dependence of the structure constant will be given by, well, we first have to pick NL out of n possible colors to distribute over sigma 1 and sigma 2. And this will give a dependence in n minus n of L factorial as a function of n in the number of such pairs. We have to distribute this number of combinations over permutations which are chosen with active colors n sigma 3 out of n. So we have n minus n sigma 3 entries over which we have to distribute the previous choices. Now this ratio is a polynomial of order nl minus n sigma 3. And therefore, the structure constant is a polynomial of that degree. So the number of active colors in the pair minus the number of active colors on the right-hand side determines the degree of the polynomial. Now, is there a relation between the degree of the polynomial and the degree q we introduced before? To establish that relation, we need two lemmas. So first, let's associate a graph to a factorization in transpositions. So if we have a list of transpositions, which has the transposition I, j, then we connect the point I and j in the graph associated to the factorization. So then if we have a minimal transposition, it will just consist of graphs which are disconnected for each cycle. But we have now a lemma, which one can prove by induction, that a transposition is minimal, a factorization is minimal if and only if the associated graph has no closed circuits. So if there is a closed circuit in the graph, then the factorization is not minimal. So this lemma is proven by induction. The second lemma says that q of alpha plus q of beta is equal to q of alpha beta only if all of the active colors in alpha and beta are also active colors in alpha times beta. Indeed, suppose that there is a color pair such that alpha of I is j and beta of j is I, such that there are colors that are not in A alpha beta, but that are in A alpha comma beta. Then if I make the graph, the minimal graph of alpha and the minimal graph of beta, then there will be an exchange of elements I to j and j to I, such that, in fact, the product of the minimal transpositions of alpha and beta is not minimal for alpha times beta, and therefore q alpha beta is smaller than q alpha plus q beta. So there will be a closed circuit, and by the other lemma, we will not have a minimal transposition. So we will not have an addition of degrees. But now we can conclude something about the structure constants. So if q alpha plus q beta is q alpha beta, then the active colors in alpha beta are all of the active colors in alpha and beta. And therefore, we will also have that the number of active elements in the set alpha beta is equal to the number of the active elements in alpha beta. And therefore, the structure constant f will have a degree equal to 0. In other words, the structure constants will be independent of the order of the symmetric group. You have discovered the ring structure, which is sort of independent of n. We conclude the following. There is a filtration of the center of the symmetric group algebra, which is given by the degree q. And then secondly, the filtration gives rise to a graded algebra, in which we restrict on the right-hand side to results that respect the degree. And then thirdly, if we do that, then this graded algebra has structured constants which are independent of n. This graded algebra I'll call the Farahat-Higman ring. Let's finish by giving an example. So if we do the ordinary product in the usual symmetric group algebra of the single 3-cycle conjugacy classes, then we get 2 times C33 plus 5 times C5 plus 8 times C2 square plus 3 times n minus 8 times C3 plus n times n minus 1 n minus 2 over 3 times the identity conjugacy class. So which terms to preserve the degree? Here we have degree 2 plus 2. And here on the right-hand side, we have degree 4. So this does satisfy degree conservation. Another one of degree 4, which does satisfy degree conservation. Then degree 2, it doesn't. Then we have degree 2, it doesn't. And then we have degree 0, also doesn't. So the filtered algebra indeed has n independent structure constants. But note that this statement doesn't go both ways. There are structure constants which are n independent, but which do not preserve the degree. This finishes our discussion of the example and of the construction of the graded Farahat-Higman ring inside the symmetric group algebra.